We're turning our attention now to the physics topic of thermodynamics. Now, the root for thermo means temperature and dynamics means motion. So thermodynamics is the branch of physics that studies atomic motion related to temperature. Now, to start everything off, we need to talk about general atomic theory. This is where we talk about the general behavior and motion of atoms and molecules. This will become much more, the reason why we need to go on the atomic level becomes more apparent when we actually define temperature in a couple of videos. But for now, let's actually learn about what we mean by this atomic theory. Well, in classical physics, we dealt often with objects that moved in a straight line, like a block of ice moving across a frictionless surface. Or sometimes we would deal with projectile motion, like a ball being thrown through the air. On the atomic level, things are not quite that simple because a molecule moving through the air has billions upon billions of molecules in the way. It'd be like throwing a ball through a pool pit, a ball pool pit. So it doesn't work quite as well. In fact, this is more like what the motion of an individual molecule would look like. It would move along and then hit another molecule and then move along in another direction and then hit another molecule moving in a different direction, move in another direction, bounce off, bounce off, bounce off. And so it just becomes totally random. In fact, the no true, sorry, let me say that again. It is impossible to predict the exact motion of an individual molecule. It is impossible because it's going to hit things and then bounce off in a different direction, and it's truly random. The scientist who discovered this, by the name of Robert Brown, discovered it by taking little specks of pollen and putting it in water. Now, the water looked to be completely still. There was no movement at all. But when he put the tiny flecks or the specks of pollen in the water, he noticed that the pollen would move around in this random motion. And so this random motion that we are talking about is now what we call Brownian motion. It's the random paths, the random nature of the path of individual atoms and molecules. Now, on a microscopic scale, we can actually look at see more or less the arrangement of molecules based on their state of matter. So a solid, which you have here in figure A, all the atoms or molecules are arranged in some lattice, in some structure that gives it stability and rigidity. But when you get to a liquid, the rigidity is gone. It's no longer in a lattice, but the molecules still kind of hang around together. They're just broken apart and free to move around each other. And so because of that, it becomes a fluid and thus a liquid. But if it becomes a gas, which we see on the right in figure C, that's when the molecules start to separate from each other. And if they separate from each other and move off in all sorts of directions, it's no longer tangible. You can't touch it like you can a solid or a liquid. Well, at least not noticeably to human perception. But all these molecules move around in the air. They're not attached to each other. They're not sticking to each other. They're just moving off on their own. Now, when we deal with things on the atomic level, it doesn't really make a lot of sense to talk about things in kilograms. For example, a hydrogen atom has a mass of about 1.6605 times 10 to the minus 27th kilograms. That's about the mass of a hydrogen atom. That's extremely small. So it doesn't make sense to use kilograms as our mass unit. So now we're going to introduce the unified atomic mass unit. which is just the symbol U. Now, one of the most stable and critical elements in our everyday life is the carbon-12 atom. In this carbon-12 atom, you have 6 protons, which are positively charged, and 6 neutrons, which are neutrally charged. There's no charge at all to them. That's what makes up the nucleus, and so it's called a carbon-12 atom because it has 6 and 6. And since it's one of the most important elements in our lives, we define 12 atomic mass units to be exactly the mass of a carbon-12 atom. So as a result, one atomic mass unit would be a 12th of that, and it comes out to be about the mass of one proton, which is where I got this number. One proton would be a hydrogen atom. So one atomic mass unit would be 1.6605 times 10 to the minus 27th kilograms.